All right, hello there, physics students, and welcome to this video on polarization of light and how pigments work with colors. Okay, we're going to start this video with a little magic trick, or is it magic? I don't know. Take a look here. I've got two lenses, okay? These are just like sunglass lenses, all right? Two of them, and you can see when I stack them up, you can clearly see through them. But when I rotate these, okay, and that's all I'm doing. I'm rotating one. You can see that this becomes completely opaque. You can't see through this at all. But if I keep rotating, then you can see through them again. Okay, rotate some more and completely opaque. I know you're thinking to yourself, well, how is that possible? And why is it even useful or desirable to have lenses that behave this way? Well, the first thing that, if we're going to understand what's going on there, the very first thing that we need to understand is that light is what we call an EM wave. This is an electromagnetic wave, EM wave. And what that means is that we have an electric field oscillating up and down in the vertical, but in the horizontal, and I'm going to butcher this, okay? So this is going to be not my best diagram, but here we go. I'm trying to show you that light is actually a two-dimensional wave. It oscillates up and down and side to side. Okay, and that's what this really bad art is supposed to do here. Okay, so the red part of this wave, this is the E. This is the electric field line, the field and how it's oscillating. The yellow part of this wave, this is the magnetic field. Magnetic. Okay, and this E is the same E that we learned about, a couple of units back when we were doing electricity. This magnetic field is also called the B field, okay, and it's a vector as well. So if this wave was coming straight at you, so if I have a single beam of light coming straight at you, a single ray of light coming straight toward you, then what you would see is you would see the light wave is oscillating up and down, okay? It's oscillating up and down, and it's oscillating side to side. Okay? It's a two-dimensional transverse wave. So light is a two-dimensional transverse wave. Okay, light is polarized when one of these waves is missing. So if the side-to-side light is blocked, then you just have the up and down. And vice versa. If the up and down is blocked, then you just have the side-to-side light. So many different surfaces, when they reflect light, they reflect polarized light. So you'll have the two-dimensional wave. So if you have a person fishing, then you have a two-dimensional light wave coming in here, reflecting off of the water. Okay, so this is the light ray. It's a two-dimensional transverse wave, and it's being reflected off of the water and into the person's eyes. But what happens is that the water, when it reflects the light ray, will only reflect the part that is moving side to side. Okay, it only reflects the side to side part, so that the water will absorb the up and down part of the wave. The up and down part of the wave gets absorbed, and the side to side part of the wave gets reflected. Okay, so that's what glare is. And the reason that if you fish, you want to wear these things called polarizing sunglasses. Okay, this is a polarizing lens. Well, what does it do? How is it designed to help this fisherman? Well, polarizing sunglasses have many, many very small black lines, straight up and down black lines. And what those do, now the gaps between them are on the order of lambda, which is the wavelength of light, okay? So we have very small gaps between them. So that what happens with this lens does is it blocks half of the light. So when you have a light ray coming in, it's oscillating up and down, and it's oscillating side to side, correct? So when the light ray goes into this, only the up and down part of the light ray passes through. Okay? The side to side ray, the side to side part will get blocked by the black lines. So if our fisherman is wearing polarizing sunglasses, if he's got some nice shades on, okay, that are polarizing, what will happen is that the polarizing lenses will block this side to side reflected light, and the fisherman really just wants to see the fish that's down here, right? The fisherman wants to see this fish, and there's light coming off of the fish up through the water. Okay? So the glare off of the water will be blocked. That's what polarizing lenses do. They block the glare. Okay, there's lots of reasons you want to have a polarizing lens. If you're a photographer, what the polarizing lens can do is it can block the glare off of glass. It can block glare off of any type of object. Okay, pilots use them because it blocks the glare off the clouds. Okay, when light is reflected off of a cloud, a lot of times it's reflected and it's polarized. And if you have the polarizing sunglasses on, then it will eliminate the glare. It will eliminate the glare off of the cloud, and you can see the clouds better. You can just see everything better because it's eliminating the glare. Okay, so let's talk about pigments and how they work. We already know that a single ray of white light contains red, green, and blue. Those are our three primary colors of light. Okay, so we bundle these three together and we get white light. All right. So, how do pigments work? So, if I have, let's say I've got, I don't know, a yellow folder sitting right here. Now, we know that this looks yellow. All right. So, what colors make yellow? What colors are being reflected off of this book? So, when this white light ray is reflected from a yellow folder, it's going to reflect red and green because red and green make yellow. Okay, if you see yellow light, it's because red and green are entering your eye. All right, so red and green make yellow. So what happened here? What did this pigment actually absorb? Okay, it absorbed the blue. It eliminated the blue. Okay, the primary colors of light are red, green, and blue. Okay, pigments subtract light, just what we saw in our example here. So each of the primary pigments absorb one of the primary colors of light. Right? So what are the primary pigments? Okay. The primary pigments are yellow because yellow absorbs blue, reflects red and green. Cyan absorbs red, reflects green and blue. Okay, and magenta absorbs green and reflects red and blue. Okay, so here's a typical type of test question. What color is produced when yellow and cyan pigments are mixed? Okay, so I've got two paints down here. I'm going to mix these together. What color am I going to get? So after I mix these, I have red, green, and blue light coming in, going to strike this surface. All right. So what does yellow do though? Yellow absorbs the blue, doesn't it? Okay. So we've eliminated the blue. Okay. There's no more blue light that's going to come off of this surface. Okay. And what is cyan? What is cyan? Cyan is blue and green, and so it eliminates the red. Okay, so cyan absorbs red. So if we mix yellow and cyan, we are going to see green. All right, so we've got magenta. In this next example, we have magenta light is being shown onto a green dress. Okay, what color does the dress appear to be? So a magenta ray of light is really made up of, so I've got a magenta ray of light, and it's really made up of red and blue. Okay. Now, if you're seeing green, you're not seeing the other primary colors. The other primary colors are red and blue. So green absorbs red and blue. You are seeing black. Okay, all color is absorbed. If that happens, what gets reflected off of here is black. Really some pretty cool stuff today. I hope you have enjoyed this video. I apologize for the bells and the announcements, but such is life here at the school. Thanks for watching, and we'll see you in the next video.